When you've completed this lesson, you should be able to understand the concepts of ratio, proportion, and percent, as well as solve problems that involve ratio, proportions, and percent. Photonics technicians need to work with these things because, for example, in scale drawings, you'll encounter scales of 1 inch to 400 feet. Or in beam divergence problems like this one, you'll have a formula of the square root of A1 over L1 is equal to the square root of A2 over L2 that relate the beam's cross-sectional area to the distance along the beams. Here's an example scenario that photonics technicians might encounter. Suppose you have a far-field beam from a carbon dioxide laser that appears to come from a point source within the laser cavity. At a distance of 3,000 meters, you measured the irradiance at 35.6 watts per centimeter squared. What would be the irradiance at a distance of 8,000 meters? And if the beam image is circular with a radius of 0.8 meters at 8,000 meters, what is the total power of that beam coming out of the laser? We'll return to this problem after reviewing some of the skills in this module. Ratios are just quantitative comparisons of objects and values. Let's consider these examples. Suppose you have Bill and Jill. Okay, Bill is twice as old as Jill. So the ratio of Bill's age to Jill's age is 2 to 1. Or we could write that as 2/1, or 2 divided by 1, or 2:1. So we know if Bill is 2 years old, then Jill must be 1 year old. Or if Bill is 10 years old, then Jill must be 5 years old. All right, that's a pretty simple one. Let's take one that's a little bit more technical. Suppose you have a large driven gear that has 4 times the number of teeth as a 10-tooth drive gear. That means the gear ratio is 40 to 10. Or we can write that as 40 over 10, or 40 divided by 10, or 40 with a colon and then 10. And you notice that we can reduce these ratios to 4 to 1. Now there's different ways to express ratios, as you've seen in the previous slide. So we could say that Bill is twice as old as Jill, and any one of these would communicate that. We can have our driven gear has 4 times as many teeth as the drive gear, and any one of these would communicate that. Or we could have donuts are on sale at half price, like 1 to 2, or a half, or 1 divided by 2, or with a colon between it. Sometimes, though, the ratios we form have units in them that don't match. For example, you may have 15 minutes over 1 hour, or 2 teaspoons to 4 cups, or 3.5 centimeters to 1,000 meters. In that case, you could use a unit ratio to convert to consistent units. For example, 15 minutes per hour, we could multiply by 1 hour over 60 minutes. This is a unit ratio that you've seen in a previous module. And you pull out the values, 15 times 1 and 1 times 60, and the units over here, and you notice that all the units will cancel, leaving you with a 15 to 60 ratio, or which we can reduce to 1 to 4. This only works when the quantities are related. For example, in our example here, we had 2 time quantities. In the second case up here, we could do the same thing with, these are volume measurements for baking. And here, these are length measurements, centimeters and meters. So we could multiply each of those by a unit ratio and leaving only the numbers as a result. We always want to reduce the fraction to its lowest terms, as we did here. The result was 15 over 60, but we could see that if we could divide both numerator and denominator by 15, we would end up with 1 to 4, which is what we've done to reduce that to the lowest terms. Sometimes the units in a ratio are not related. Not all time units, or not all volume measurements, or not all distance measurements. For example, here's 360 miles per 8 hours, or the ratio of 14 gallons to 3 minutes, or $26,995 to 10 years. You could imagine where all those ratios might appear. In such cases, the numerical part of the ratio can sometimes be reduced to lowest terms. So we'll take the 360 miles divided by 8 hours, and we can reduce that to 45 to 1 miles per hour. Or you can use unit ratios to convert to different units, for example, and you've seen this also in the previous modules. We can take 14 gallons to 3 minute ratio, multiply it by a ratio of 1 minute over 60 seconds, which will effectively change the minutes to seconds because we know the minutes will cancel, and multiply by a 1 cubic foot per 7.48 gallons, noting that the gallons will cancel, leaving us with cubic feet. And so we multiply the values together and the units together, and as we planned, cubic feet and seconds are the only thing that remains in the units, and we're left with 14 over 1346.4 feet cubed per second, or if we evaluate that ratio, it's 0.0104 cubic feet per second. Now, a percent is just a special ratio, and it compares the number of parts to 100 equal parts. So, out of 100 pencils, for example, if 10 are red, then the ratio of red pencils to the total is 10%. You probably figured that out without using your calculator. Or if 37 are green, then the ratio of green pencils to the total is 37 to 100. 37 green pencils to 100 total pencils, which we can write as 37 to 100, or as we evaluate it out, we know it's 37% green. Percents are pretty easy to work with, but you don't always have ratios that are compared to 100. Sometimes the ratios are compared to other numbers of equal parts. For example, suppose we have 1 out of 6 equal parts. What percentage is the 1 part? Well, we write that ratio as a fraction and convert it to a percentage. So we have 1 to 6 is the ratio, and we can just multiply it by a unit ratio of 100% to 1 and end up with 0.16667 times 100%, or 16.7%. Now, this is the mathematically correct way to handle the conversion. You know that you're just really multiplying 1/6 times 100% is probably the way you're used to seeing it, and that's quite all right. So 1 out of 6 is the same as 16.7%. Now, what would the percentage be for 3 out of 6 parts? Can you think through that? Well, without actually showing it on the screen here, I bet you can already know that 3 out of 6 is going to be a ratio of 0.5 times 100%, which is 50%. Good for you. Now, proportions are equal ratios, and the concept of a proportion is very important in mathematics and very important for you in solving your problems in photonics. So we have, for example, 2 ratios, 4 over 2 and 10 to 5. Those are said to be proportional because they're equal. 4 over 2 is equal to 10 over 5. They both have a value of 2. So here are some equal ratios that are all proportional. 4 to 2, 10 to 5, 8 to 4, 12 to 6, and 20 to 10. Interestingly enough, these are also proportional. Can you tell what the difference is? I've just inverted the numerators and denominators on all of them. So 2 to 4, and 5 to 10, and 4 to 8, and 6 to 12, and 10 to 20, and so on. Those are also all equal ratios. Ratios that are not equal are not proportional. So, for example, the ratio of 2 to 4 is not equal to the ratio of 1 to 3. So we say that 2 to 4 is not proportional to 1 to 3. Now, equal ratios have a nice thing called a proportionality constant. They equal that constant. And so, as we saw earlier, 4 to 2 and all these other ratios all equal 2. So here's an example. Suppose we have a spring that's rated by its spring constant, the ratio of force needed to stretch the spring a certain distance. You'll see that that constant is equal to the ratio of F1 to D1, or F2 to D2 if the string is stretched, and so on. So we have lots of different proportions that can come out of that, but it's always equal to K if the spring maintains its elasticity. So let's look at this spring a little more closely now. A certain spring requires F equals 10 pounds to stretch 2 inches and a force of 20 pounds to stretch 4 inches. So we can set up two different ratios, right? 10 pounds to 2 inches and 20 pounds to 4 inches. And I believe you can see that the value for both of those is 5 pounds per inch. There's a constant of proportionality present in this relationship. Interestingly, you'll notice if we plot the distance of the stretch versus the force, as the distance gets bigger, the force gets bigger, and they all fall on a straight line. What do you think you know about that straight line? It looks a little bit like the slope, doesn't it? We're going to determine a little later in this course the slope of the graph of the force to the distance is, in fact, the spring constant. Now let's return to that opening scenario where we had the beam being spread by an angle theta. We note that there's a ratio called tangent that you'll learn about in a later module in this course, which is equal to the opposite over the adjacent side of a right triangle. And on this particular triangle up here, we have the angle is theta over 2. If the entire angle of the beam spread is theta, then half of it will be theta over 2. And the tangent of that angle equals the opposite side of that triangle over the adjacent side, the side that's adjacent to the angle. And so we set up that proportion here, that the tangent of the ratio of those two sides is always going to be, for example, for the small rectangle down here, d3 over 2, half of d3 divided by the distance, the adjacent side would be 3,000 meters. Or for this big triangle, it'd be d8 over 2, half of that divided by this distance, which is the 8,000 meters. So we can see that the divided by 2's will cancel out, and what we're really left with is two ratios, d3 over 3,000 meters equals d8 over 8,000 meters. And we can rearrange that by multiplying and dividing by the different terms and end up with the d3 over d8 is equal to 3,000 to 8,000 meters, or the constant of proportionality, 0.375. Now, we're told that the irradiance E varies inversely with the target's cross-sectional area. And the cross-sectional area is going to be pi divided by 4 times the diameter of the beam squared. So we can write that the irradiance from at position 8 to the irradiance at position 3 is equal to inversely, so we'll have the area of at position 3 divided by the area at position 8. Notice that because it's an inverse proportion, that we've got reversed subscripts on our formula. So now we can substitute in the area calculations as pi over 4 times the diameter of position 3 squared, and pi over 4 times the diameter at position 8 squared. You'll notice that the pi over 4's will cancel, and then we're just left with the ratio of the d3 squared to d sub 8 squared is equal to the ratio of the irradiances at e sub 8 over e sub 3. Again, notice that they're inversely proportional. We can just solve for the irradiance at position 8 and end up with d sub 3 over d sub 8 squared times e at position 3. So now let's substitute in our irradiance that we were given and the constant ratio we found and square that and multiply that by the input, the irradiance we measured at E3, and that was 35.6 watts per centimeter squared, and we end up with a 5.01 watts per centimeter squared. So the beam's irradiance at that far position is 5 watts per centimeter squared. With a beam diameter of 160 centimeters, we're asked to find the power at position 8. To do that, we multiply the power of the beam is equal to the irradiance times its area. Okay, and so the irradiance at 8, which we just figured out, and the area at 8, which we're going to calculate, we'll substitute in those values. 5.01 watts per centimeter squared, pi over 4 times 160 centimeters squared for the diameter, and group the numbers and the units. You know, centimeters squared will cancel, and the result will be just watts. So we're left with 101,000 watts, better known as 0.1 megawatts. That is a huge laser pulse that's coming out there. Okay, so let's look at some practice exercises to see if you can apply these skills to some real-world kinds of problems. We'll not solve all of the problems here, but we'll cover enough of them to give you some confidence to solve the rest of them by yourself. First of all, let's look at exercises 2, 3, and 4. They're all related, and so we'll just cover them quickly. What is the ratio of shaded to unshaded areas in this problem? Well, that would be the count of the number that's shaded divided by the count of the number that's unshaded, which would be 12 to 8, if you count those shaded squares, which we can write and reduce. We can divide both of them by 4, for example, and reduce to 3 to 2. So the ratio is 3 to 2, which we can write many different ways. Next we're asked, what is the percent that's shaded? Well, if we have 12 parts shaded and 20 parts total, then we have 12 to 20, and we want to multiply it times 100% to get the percent shaded, and the result is 60% shaded. And the percent unshaded is 8 parts to 20 parts, which is 40% shaded. And you'll notice that, of course, what's the sum of the percent shaded and the percent unshaded? As it should be, it's 100%. Here's a second figure. What's the ratio of shaded to unshaded? Again, how many are shaded? 4. Unshaded are 4. So we have a ratio of 1 to 1, which we can write 3 different ways. The percent shaded, you can probably know this without even thinking about it, is 4 parts out of 8 parts, which is the same as 50% shaded. And I'll bet you know already what the percent unshaded is. Sure enough, it's also 4 parts to 8 parts, which is also 50% unshaded. Okay, we got one more figure to look at. That will be the square figure that's got shaded in half. Now this one's a little more tricky because it doesn't have a number that you can count. So what is the ratio of the shaded to unshaded in this case? Well, we notice that they're equal total areas that are shaded and unshaded. We don't care what number they are. They're going to be 1 to 1 because they're both the same. So the percent shaded is clearly half of it shaded, better known as 50%. And half is unshaded, which is also equal to 50%. Here's exercise 6. Asks you to look at some solder that's made of 6 parts tin and 4 parts lead. Very common percentage. And that is, for every 10 parts of solder total, there are 6 parts of tin and 4 parts of lead. So this is just like the figures that we saw earlier. You could draw yourself a box with 10 parts in it and color in 6 of them for the tin and 4 of them for the lead, and you'll be just like the previous exercise. So in 1 kilogram of solder, how much of it is tin? Well, we'll set up a proportion equating 2 ratios. X, for the number of grams of tin that we're looking for, is related to 1,000 grams of solder. As we know, the ratio of 6 parts tin to 10 parts solder. So now we just need to solve for the unknown parts. And as you learned in your previous module about solving proportions, you can multiply both sides by 1,000. On this side, the thousands will cancel, leaving us with just the x that we're looking for. And on the right, we're going to have to multiply all these parts together. And so we're left with 6 times 1,000 divided by 10. And the parts cancel and the solder's units cancel, and we're left with grams of tin. 600 grams of tin. And of course, you'll know that the question next will be how much of it is lead. So again, we'll set up a proportion equating 2 ratios. As before, this time the grams, X will represent the number of grams of lead into 1,000 grams, and 4 parts lead to 10 parts solder is the ratio that we'll equate to. So again, we'll solve for the unknown part of the proportion by multiplying both sides by 1,000. We'll be left with this value, 4 times 1,000 divided by 10, with the units canceling again. This time we'll have 400 grams of lead out of 1,000. Now, exercise 7 asks you which of the ratios is proportional to the ratio 40 to 5? Well, proportional ratios are equal, so test that theory with each ratio. So is 20 to 10 equal to 40 to 5? Well, we multiply both sides by the denominators, or cross multiply. So we multiply 20 over 10 times 10 and 5, and 40 over 5 by 10 and 5. The 10s will cancel, and we'll be left with 20 times 5, and the 5s will cancel, and we'll be left with 40 times 10. You see now why we call it cross multiplying? That's the same as multiplying 20 times the denominator of the other fraction, and 40 times the denominator of the first fraction. That's a shortcut that we'll be able to use instead of going through this process up here. So we're left with 20 times 5 is 100, and 40 times 10 is 400. These are not equal, so the answer is no. 20 to the 10 is not equal to 40 to 5. Here's a second ratio, 8 to 1. Is that equal to 40 to 5? Well, again, we'll cross multiply. 8 times 5, is that equal to 40 times 1? 40 equals 40, so yes, 8 to 1 is equal to 40 to 5. Those proportions are equal. A third example is 5 to 40 equal to 40 to 5? If we just invert one of them, does that make it equal? So we'll cross multiply again, just like we did before. 5 times 5 and 40 times 40, and it's pretty easy to see that those are not equal, so the answer is no. 5 to 40 is not equal to 40 to 5. And the last one we can look at is 80 to 11 equal to 40 to 5? Might be close. 80 times 5 and 40 times 11 is 400 to 440? No, not quite equal. But the answer is no, they're not equal. Now, what is the constant of the ratios 1 to 8 and 8 to 64? Well, if the ratios are proportional, then the value of either ratio is the constant of proportionality. So let's first check to see, are those ratios proportional? Just like we did in the previous exercise. Is 1 to 8 equal to 8 to 64? Cross multiply. And sure enough, 64 equals 64, so yes, they are proportional. And the constant of proportionality would be the reduced fraction that we could get out of those, and that would be 1 to 8, or a value of 0.125, which is actually also a fraction. It's a decimal fraction. Let's look at exercise 12, which asks us to look at a scale drawing that is drawn at 1/4 inch to 1 foot in real life. So we're asked, what is the ratio of the scale drawing? Well, we can write it in many different ways. It can be 1/4 inch to 1 foot, or 1/4 inch to 1 foot. Or we could change the units and say it's 1/4 inch to 12 inches, or 1 inch to 48 inches. Right? We multiply both of them by 4 and get rid of the 4 and get 1 inch to 48 inches. Or since we have both of them are inches, we can just say the ratio is 1 to 48. So this scale drawing here is 1 to 48. Now, how long of a line would represent a 24-foot wall? Well, we're going to have to apply our proportion on our ratio. So we have set up a proportion for the drawing dimension to the real life dimension is equal to the proportion of the scale of the drawing, which is 1 to 48. Let's substitute our values in. So we have a 24-foot wall in real life, which we then can multiply out and solve for the drawing equals 0.5 feet, or 6 inches. So a 6-inch line on the drawing would represent a 24-foot wall. We can go the reverse. How long would a duct be that's depicted by a 9.5-inch line on the drawing? Well, now we just have a different ratio. We have the real life to the drawing is equal to 48 to 1. All right? Be sure you take note of the relationship. So we have a constant of proportionality, right? So we substitute in our drawing dimension, which is 9.5 inches. Multiply that out, and we end up with 9.5 inches times 48, which is 456 inches, or 38 feet. And here's a good exercise. A hand-operated winch features a worm gear and a drum gear with a 41 to 1 gear ratio. All right, buckle your seat belts. This is going to be a good problem here. For a 1.5 inch diameter drum, how many turns of the crank are needed to reel in 18 inches of cable? Okay, here we go. Each turn of the drum is one circumference. And a circumference is equal to pi times its diameter, which we're told is 1.5 inches. So the circumference is 4.71 inches. All right, we're on the roll now. We need 18 inches, and each turn is going to flop off 4.71 inches. So how many do we need? Well, we divide those two numbers, 18 into 4.71 per turn, and we get 3.82 turns of the drum. And now, how many turns of the crank are needed is the question. So not how many turns of the drum. So that means how many turns of the worm gear in the ratio to the turns of the drum we're given is 41 to 1. So we can set up this proportion. And substitute in our known value of 3.82 turns is the number of turns of our drum. So how many turns of our worm gear will we get out of that? If we multiply that out and solve for turns of worm gear, we have 41 times 3.82 is 157 turns. So if you can turn that crank at 40 turns a minute, that's really cranking. How long would it take you? Well, 40 turns per minute is another ratio, isn't it? 40 turns over 1 minute equals 157 turns at X number of minutes. And we want to find out what the X is that will make this thing work. So we cross multiply, get 40 turns times X equals 157 turns times 1 minute. Then we're going to solve for X by dividing both sides by 40 turns. And we have 157 turns divided by 40 turns times 1 minute, and the result will be 3.9 minutes. So it'll take you almost 4 minutes to reel in 18 inches of cable with this worm gear. And that concludes our treatment for ratios and proportions. I know that now you're going to have enough confidence to solve the rest of those practice exercises and use these skills in your other courses. We'll see you next time.